In this video, we're going to talk about acids and bases and how to make buffers. So if we look at an example where we have a strong acid and a strong base, we have hydrochloric acid plus sodium hydroxide gives us water plus sodium chloride. So if we take this and write our ionic equation from it, so we break apart everything that is aqueous into its ions, we get so we have the hydrogen and the chloride ions and the sodium and the hydroxide ions from our hydrochloric acid and our sodium hydroxide. Water is a liquid, so we can't break that up. And then we have sodium and chlorine. So if we cancel out everything that shows up on both sides, we have sodium and we have chlorine. So all that we're left with is the H plus the OH negative gives us water. So that's our net ionic equation. So since we're just forming water that has sodium and chloride ions floating around in it, if we were to measure the pH of that, assuming this is pure water, we would have a pH of 7. So if you're reacting a strong acid with a strong base, then when we get water and the ions that are dissolved in water as our product, the pH of that should be pretty close to 7. If we take a weak acid and a strong base, we know that weak acids and weak bases don't dissociate completely, so we're still going to have some of the acetic acid ion if that's our weak acid. So if we assume complete dissociation, we know that the only thing that's going to cancel out is the sodium, so we're left with acetic acid plus hydroxide gives us water plus the sodium plus the acetate ion. And we can show that because acetic acid doesn't dissociate completely in solution, so we can't write it as its ions. But sodium hydroxide is a strong base, so it does dissociate completely. And sodium acetate is ionic, so that's going to break apart into its ions. But the only thing that appears on both sides is the sodium. So we still have acetic acid in there, and then we have our hydroxide ion. Since the base is stronger than the acid, the pH of the solution is going to be greater than 7. If we have the opposite scenario, we have a strong acid and a weak base. If we write our net ionic equation, a strong acid dissociates nearly completely, so we would have H plus and Cl negative ions. Ammonia is a weak base. And for our NH4Cl, that is ionic, so we're going to get, even though there's no metal in ammonium chloride, the ammonium ion functions as the cation and the chlorine functions as the anion. So it functions like an ionic compound even though it's not actually ionic. It doesn't have a metal there. So if we cross out the things that appear on both sides, the only thing that we can cancel out is the chlorine. So since our acid is much stronger than our base, our pH of this solution should be less than 7. Well, what if we now take a reaction where we have a weak acid and a weak base? Well, our weak acid and our weak base don't dissociate very much in solution. They will dissociate a small amount, but nowhere near enough that we can assume that they would be mostly ions. So the only thing that actually breaks up into its ions is the ammonium acetate here. So we would get NH4 positive ions and CH3 CO2 negative ions. But the acetic acid and the ammonia don't break apart into their ions. So this equation here is going to be our final equation. If we want to write it in ionic form, we can break the ammonium and the acetate apart into their ions, but we still essentially have the same thing. So, since one isn't really any stronger than the other, and we don't have a non-ionic equation that shows us that we have more acid or base, we can't really predict what the pH is. So we're going to talk about how we would calculate the pH of this solution. So let's take an example where we just have acetic acid and water. So if we react acetic acid with water, the water gets a proton from the acetic acid. So we get H3O plus, which is our hydronium ion, and acetate. Well, if we have both of these ions here, and we add a substance that provides something we already have, for example, if we add more acetate, if we think back to Le Chatelier's principle, what we're going to do is drive the reaction in the other direction. So say, for example, we add more acetate, we're going to drive the reaction back towards the reactants. If we add more acetic acid, we're going to drive the reaction back towards products. So if we add more of the acetate ion, we can force the reaction to go back towards our reactants. So we use this principle to make buffer solutions. A buffer solution is a solution that contains a weak acid and its conjugate base. So some examples of that would be something like acetic acid and the acetate ion. Now, it's not that we're putting the acetate ion by itself in solution, because that doesn't exist. You can't go into the lab and get some acetate off the shelf. What you can get is something like sodium acetate, which contains the acetate ion, and since this is ionic, it would break apart into the sodium ions and the acetate ions in solution. So the sodium by itself is just going to be a spectator ion. It doesn't really do anything. And the acetate will provide the conjugate base of the acetic acid. Hydrofluoric acid and the fluoride ion would be another example. We don't really actually use that one because hydrofluoric acid is extremely dangerous. In fact, just getting a drop of it on your skin can actually kill you. So we're obviously not going to use that as a buffer. Better example would be the ammonium ion and ammonia. So that is an example of a buffer. We have a weak acid in the conjugate base, or something like our phosphate ions. So we can take the weak acid and the conjugate base of that weak acid. So if we get a buffer solution, because of that common ion effect, a buffer solution will resist drastic changes in pH. Because what's going to happen is, for example, if we take our acetic acid and our acetate buffer, if we add a bunch of acid, the acetate ion is going to react with it and drive the reaction back towards our towards our reactants. So if we add a bunch of acid, which is going to contain H3O plus, we're going to go back towards the reactants to neutralize that acid. If we add a bunch of base, then the acetic acid is going to react with it, and we're going to go back towards the products and form more of the product. So, for example, if we have H3O plus in our solution, and we have the conjugate base, and then we have our acetic acid, if we add OH to it, what's going to happen is the acetic acid is going to react with that hydroxide ion. So the hydroxide ion can get this proton here, and we get water and more of the acetate ion. So we've driven the reaction back towards the products. If we add H3O plus, then that's going to react with the acetate, and we're going to go back towards our reactants. So whatever we add, whether we add acid or base, there's something in solution that will react with it and essentially neutralize it. Now this only works up to a point. If you add too much of your acid or your base, or if you add too strong of an acid or base, then you can start to change the pH a little bit. But as long as you're not adding something that is past the capacity of the buffer, it will reduce the effects and it will resist any drastic changes in pH. So we add OH to a buffer solution, some of that weak acid gets converted back to the conjugate base. If we add H3O plus, some of the conjugate base is converted to weak acid. So as long as we can keep that concentration ratio of weak acid to conjugate base fairly close to the original, we can keep the pH from changing too much. So how do we know what the pH of a buffer solution is? Or if we want to make a buffer solution of a certain pH, how do we know how much of our weak acid and our conjugate base to add? Well, there's actually an equation that can help us calculate those things. So we learned when we write the acid dissociation constant for a strong acid, or for any acid really, we have H3O plus, our conjugate base, over the acid. So we can rearrange that and solve for H3O plus. Now this top portion here shows you how we can derive this equation. I'm not going to go through that because I'm not going to ask you to derive the equation. I just show this so you can see that we didn't just pull the equation out of thin air. It does come from somewhere. There's a mathematical way to get to it. But what I really want you to be familiar with here is the equation. So this is called the Henderson-Hasselbalch equation. If we take the pH, that's equal to the pKa plus the log of the concentration of the base over the concentration of the acid. So pKa is the negative log of Ka. So just like pH is the negative log of H3O plus, pKa is the negative log of Ka. So whenever you have a lowercase p before some constant or some value, that's a mathematical way of writing the negative log. So pK is the negative log of Ka, pH is the negative log of H plus or H3O plus. So let's take this equation and use it to calculate the pH of a solution. We want to calculate the pH of a solution containing 0.22 molar acetic acid and 0.13 molar sodium acetate. And we're given the Ka of acetic acid, which is 1.8 times 10 to the negative fifth. So we're told which one is our acid because it's in the name. So we can figure out from that the sodium acetate must be the conjugate base. So our Henderson-Hasselbalch equation asks us for the pKa when we start plugging things in. So we're going to need to calculate pKa. So we have pKa is equal to the negative log of Ka, which is the negative log of 1.8 times 10 to the negative fifth. So if you put that into your calculator, you should come up with 4.74. So we can now take the Henderson-Hasselbalch equation. So pH is equal to pKa plus the log of base, the concentration of the base, over the concentration we don't want to highlight that. We want the pen. Here we go. So pH is equal to pKa plus the log of base over acid. So we can plug in the pKa that we just calculated plus the log of concentration of the base, which is sodium acetate, is 0.13 molar. And the concentration of acetic acid is 0.22 molar. So what I would recommend doing, since we just calculated the pKa, and this is going to be rounded off, is when you put this into your calculator, keep that value in there, and then just type plus log, and your calculator should open a parentheses, 0.13 divided by 0.22, close your parentheses, and hit enter. That way you will get an exact answer and not an answer that's affected by the rounding when we came up with the 4.74. So if you put into your calculator 4.74 plus log of 0.13 divided by 0.22, you should come up with 4.52. So let's take a look at another example here. We want to determine the number of moles of sodium acetate that must be added to 250 milliliters of 0.16 molar acetic acid in order to prepare a pH 4.70 buffer. So this time we have the pH, and we want to know how much of one of the components we need to add. And this is something that we would need to calculate in lab sometimes. We might have a situation where we know what pH we want, and we need to figure out how much of the acid or the base to add, or we might want to know the ratio so that we can figure out how much acid we should add in relation to the amount of base. This time we're given a molarity of our acid. Now you'll notice the Ka is slightly different, but if you look back at the last slide, it was 1.8 times 10 to the negative fifth, and in this case it's 1.76. So that's just a rounding difference. Sometimes you will see slight differences in the constants based on what source you look at. So if you take the negative log of 1.76 times 10 to the negative fifth, you come up with 4.75, which is 1 decimal point off from the 4.74 we had on the last slide. So we're going to go ahead and use this, since this is the Ka that we're given for this problem. So we have our Henderson-Hasselbalch equation tells us pH is equal to the pKa plus the log of concentration of base over the concentration of acid. So we can plug in the pH that we want, which is 4.7. That's equal to a pKa of 4.75 plus the log of, we don't know what the concentration of our base is, so I'm just going to put the concentration of base. And we know the concentration of acid is 0.16. So then if we want to get the base by itself, so let's first move 4.75 over to the other side. We have 4.70 minus 4.75 is equal to the log of base over 0.16. So 4.70 minus 4.75 gives us 0.0. not write quite so little on the screen. So that gives us 0.05 is equal to the log of base over 0.16. So the way that, and that's supposed to be a negative 0.05. So the way that we get rid of a log, the inverse of a log is 10 to the power of whatever we have. So to get rid of a log, we would take 10 to the negative 0.05, and that gets rid of our log there. So we have the concentration of base over 0.16. And then I want to get base by itself, so I'm going to take and I'm going to draw a line here so that this isn't running into each other. So we have base is going to be equal to 10 to the negative 0.05 times 0.16. So if you multiply that out, you take 10 to the power of negative 0.05 and multiply that times 0.16, we should come up with the concentration of the base is equal to 0.141 molar. Now, if we think back to the definition of molarity, molarity is equal to moles over liters. So if we want moles by itself, we would take moles and we would multiply molarity times liters. So if we convert 250 milliliters to liters, that's 0.2500 liters. So we're going to take 0.141 molar times 0.2500 liters. And if we multiply that out, we come up with 0.035 moles of sodium acetate that we need to add here. So we're going to stop here, and we will pick up with some more calculations with buffers in the next video. So I will see you in class.